In this video, we solved problem 14.7.031 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're asked to use spherical coordinates to find the volume of the solid, and we're told that the solid lies inside x squared plus y squared plus z squared equals 81. So that is a sphere centered at the origin with a radius of 9. And it lies outside this. This actually represents a cone, and it's above the xy plane. So what I would recommend you do to start this problem is first draw the solid region. That's always the first thing we do. Sketch the solid region as well as you can. And then we'll use our sketch to come up with appropriate bounds for a triple integral in spherical coordinates representing this volume. Okay, so let's start with that x squared plus y squared plus z squared equals 81. This is a sphere centered at the origin because we're not subtracting anything from the x, y, or z. And the radius of this sphere comes from using this number. This is r squared in the standard form of the equation of a sphere. So you take the square root of that to get the radius, and you see we have a sphere of radius 9. So we're talking about this. Now I'm just going to draw a sphere centered at the origin. I'll put a little line here to sort of indicate that it's 3-dimensional rather than 2-dimensional. And this intersects the x, y, and z axis at 9 and -9 for each of those. So it intersects down here at z equals -9. It intersects back here at x equals -9, and it intersects over here at y equals -9. Okay, so we want a solid that's inside this sphere and outside this guy. Now that's actually a cone. Maybe you're starting to recognize that equation as the equation of a cone. If you're not, that's okay. What I would do is I would take this equation, since it has that x squared plus y squared in it, I think it's probably one of my quadric surfaces. Let's take it and rearrange it until it looks more like one of the equations of the quadrics that we studied earlier this semester. The quadrics don't have square roots in them, so we'll square both sides to get rid of that square root. Now we've got x squared plus y squared equals z squared, and z is the positive square root. That's what we were told. So the z values on this surface satisfy this equation, but we want to make sure our z is always given by the positive square root of this quantity. That means that z has to be greater than or equal to 0. And if we take this equation and we rearrange it, we get x squared plus y squared minus z squared equals 0 for z greater than or equal to 0. And that is an elliptic cone. It's really more of a circular cone, but it's an elliptic cone in general. It's top half only. And remember that negative indicates the axis where that cone is going to open. Since the negative is on the z squared term, the cone opens up and down, but we're only talking about the top half. So what we would see is something that looks like that. That's where our cone would intersect that sphere. Okay, now we're talking about a solid region. We want spherical coordinates. We want to use spherical coordinates to find the volume of the solid inside the sphere, but outside this cone and above the xy plane. So keep that in mind. We actually don't want the bottom half of the sphere at all. We don't want anything inside the cone, but we want like everything outside the cone. It's like we took the sphere and then we took that cone and we cut out the cone. Yeah, it's really hard to imagine what it would look like. But on the outside, it would look kind of like this. And then when you look inside at the missing part would be that cone that we cut out. And then if you imagine continuing that, we would get that top, that little cap of the sphere. So we're trying to find the volume of this that's left. It's that part of the sphere with that cone missing. Okay. And I almost want to sketch it in here. And I guess I will. I don't really think it does it any justice. But remember, we're talking about this and not the inside part. It's that red region all the way around. So we would see that boundary over here on the other side. It's just the cone would be cut out of it. Okay, now we're asked to find the volume of that region in spherical coordinates. So in order to do that, we're going to need bounds for rho, theta, and phi. And the bounds for rho, theta, and phi can be found by using these equations. So what I would suggest you do is start by converting the given equations to spherical coordinates. And remember what your spherical coordinates conversion formulas are. X squared plus y squared plus z squared equals rho squared in spherical coordinates. Tangent of theta is still y over x, just like it was in polar coordinates. And z is rho cosine of phi. So cosine of phi is z divided by rho, which can be written this way. So you want to keep those formulas in mind when you're converting. So let's start with x squared plus y squared equals, or plus z squared equals 81. Well, using our coordinate conversion formulas, we know that this is just rho squared. So we've got rho squared equals 81, which means that rho equals the positive square root of 81, or rho equals 9. Now, rho equals 9 is just the sphere, it's just the outside, it's not that solid region. So rho is actually going to go from 0 out to 9, because we're imagining if rho goes from 0 to 9, you want to imagine a bunch of nested spheres. Rho equals 0 is just a single point, it's the origin. Rho equals 1 is a sphere of radius 1. Rho equals 2 is a sphere of radius 2. So it's like we're starting here at 0 and then we're going like out to 9. And I hate that I can't really show you via Zoom, but it's kind of starting like this, and then there's one around it, and then one around it, and then one around it. And if you're saying, well, it doesn't go all the way from 0 to 9, you're right, we don't get the entire sphere, or that entire set of nested spheres. We don't get the solid sphere of radius 9, but those are our bounds for rho. To specify the rest, like which part of these nested spheres we get, we need bounds for theta and phi. Okay, so we've got rho goes from 0 to 9, because we start at the origin and we go out to this sphere of radius 9. Now in this other one, we've got z equals this positive square root of x squared plus y squared. In order to convert these, I just need to use my coordinate conversion formulas for x and y and z. Now z is rho cosine of phi. X is rho sine of phi cosine of theta, because rho sine of phi was r in polar coordinates. Y is rho sine of phi, that's R, times sine of theta. And then there's our Z. So we can use these here to simplify this. Replace Z with rho cosine of phi. Replace X and Y with rho sine of phi cosine of theta. Rho, and then Y is rho sine of phi sine of theta. We're squaring those. Now you square each factor separately, so we get rho squared, sine squared phi, cosine squared theta. And then we've got rho squared, sine squared phi, sine squared theta. And if you're looking at this thinking that's a mess, you're absolutely right. But we've got trig functions. We've got sines and cosines everywhere. So there are probably going to be some nice simplifications. Turns out there are. So I look at this guy and I look at this guy and I say to myself, what do they have in common? Well, they both have that rho squared sine squared phi. So we can factor that out. And then remember how we simplify this. We say to ourselves, this times what gives us the first term? Well, this times cosine squared theta gives us the first term. And then we say this times what gives us the second term? That times sine squared gives us the second term. And looky here. Sine squared plus cosine squared, same angle, that's going to give us a 1. And I've got two perfect squares, and phi is always between 0 and pi, so this is always non-negative. So we can take the square root of each of these pieces separately, and we get rho sine of phi equals rho cosine of theta, or cosine of phi, excuse me. If we divide both sides by rho cosine of phi, we get 1 equals tangent of phi. What is the angle whose tangent is phi? That's pi over 4. You're saying to yourself, what does that mean? That means this cone is given by the equation phi equals pi over 4. Okay, now we need bounds for phi. If we're starting at the cone and going to the xy plane, phi is equal to pi over 2 in the xy plane. Because remember, phi is an angle measured from the positive z-axis. So phi equals 0 is here, phi equals pi over 4 is here, phi equals pi over 2 is the entire xy plane, phi equals 3 pi, or 3 pi over 4, that would be pi over 4 radians this way, and then phi equals pi is all the way down here on the negative z-axis. So if we're going from the positive z-axis to the xy plane, we're going from 0 to pi over 2. But because we're looking for the solid region between the cone and the sphere, between the cone and the sphere and above the xy plane, if he's going to start at pi over 4, that's the boundary for the cone, and it's going to go to pi over 2. Oops, I don't know why I keep doing that. So we start from pi over 4 and go to pi over 2. And of course, we're going all the way around the xy plane. So theta goes from 0 to 2 pi. This is what it looks like in the xy plane. We've got that circle of radius 9. Remember, theta is an angle that sweeps around the xy plane. It starts there and it ends there. So it goes from 0 to 2 pi. Okay, so we've got bounds for rho. Sorry, this one's a little messy on this video. Sorry, we got that. Those are our bounds for rho. Bounds for phi and bounds for theta. Now all we have to do is set up the integral and then evaluate it. It's a different problem. There we go. So the volume of that solid is the triple integral over Q of dV. And I think I will integrate with respect to theta last. Theta goes from 0 to 2 pi. Phi goes from pi over 4 to pi over 2. And rho goes from 0 to 9. And remember, dV in spherical coordinates is rho squared sine of phi. And then we'll have a d rho, d theta, d phi, and you can change the order. Multiplication is commutative, so that's fine. It just needs to match up with these bounds. Because of the way I wrote these bounds, I need rho first, and then phi, and then theta. And that's it. If we evaluate this integral, that's going to give us the volume of this guy, the volume in between that cone and inside the sphere and above the xy plane. So we'll do this one first. Integrate from 0 to 2 pi, integrate from pi over 4 to pi over 2. And phi is constant, so we can factor out that sine of phi for right now. And we anti-differentiate with respect to rho first. Add 1 to the exponent, divide by the new exponent. Evaluate from rho equals 0 to rho equals 9. And then we subtract. So I'm going to have 9 cubed over 3 minus 0 cubed over 3, which is just 0, times sine of phi, d phi, d theta. And now we want to integrate with respect to phi. Now, this 9 cubed I could write as 9 squared times 3 times 3. Just so I could simplify one of those 3's. This makes me feel better. Then I've got this 0 to 2 pi. And I want to integrate, or, well, integrate, but also anti-differentiate sine of phi with respect to phi. The antiderivative of sine is negative cosine. And we're evaluating from phi equals pi over 4 to phi equals pi over 2. And that is 81 times 3, so 243. And if we evaluate this at pi over 2, we get negative cosine of pi over 2. And then we're subtracting a negative, so that's adding cosine of pi over 4. That's just a number. The antiderivative of that number with respect to theta is that number times theta, evaluated from theta equals 0 to theta equals 2 pi. Cosine of pi over 2 is 0. Cosine of pi over 4 is square root of 2 over 2. And if I evaluate this at 2 pi and 0 and subtract, I'm just going to end up with a 2 pi. So I have 243 times square root of 2 over 2 times 2 pi. The 2's reduce. Typically we write our radical last. And we have 2 pi, or 243 pi times the square root of 2 units cubed. And what is that? That's the volume of the solid region Q, which is here. Now we could have also evaluated this volume integral in polar coordinates. That would have been fine. The bounds wouldn't have been as simple, but the integrand would have been more simple. So that's an option. I definitely would not evaluate this or try to find the integral of this in rectangular coordinates. There is nothing rectangular about that region. So spherical or spherical or cylindrical coordinates is the way to go. And I hope this was a good example and some good practice with using spherical coordinates.